Hi guys, good day. Today I'll be teaching vertical stresses, CEG 414 Foundation Engineering, and I'll start with 2017-2018 question 2B on vertical stresses. Well, before I start, I just want to explain the concept of vertical stresses, where a force is applied on a soil, and you have to calculate the effect of the force at the point on the soil. So to get a vertical stress, the formula is given by Kp over Z squared. Some textbooks use K as I1, I whatever, where K is equals to 3 over 2 pi into bracket 1 all over R over Z squared plus 1 all raised to power 5 over 2. We get this later. This is a vertical stress for a point load. It's just these formulas, that's all. And for in instances where you don't have a point load, where you have maybe a rectangularly loaded area, and you find vertical stress of this rectangle, they'll probably give you maybe in the center of the rectangle, an edge, or outside edge. We'll also deal with questions like this in this short tutorial. So to get to it, the question says figure 2b shows 2-point loads placed at ground surface. Use the application of point loads Q1 and Q2. Vertical stress increase at a point A is 2.60 kN per meter squared. Determine the magnitude of Q1, given that Q2 is equal to 260 kN per meter squared using this equation. When you check the diagram, the Q2 is given as 260 kN per meter, and the question is 260 kN per meter squared. I just have to say that this Q is a force, the point load, and it's not per meter inside, just kilonewtons. Probably an error when you were printing or from the lecturer. Vertical stress is a stress which is in kilonewton per meter squared, while the point load is just in kilonewton per time to pass across. So to start this question, back to the same equation I gave, where this is equals to K, let me use I P all over Z squared. There's a table to get influence factors, and it is dependent on R all over Z. So rather than going through the long process of writing that formula where I is equals to 3 all over 2 pi into 1 all over R over Z whole squared plus 1 to 5 over 2, just have a formula table that you can check for values. So you get to get the vertical increase at a point, they gave us as 2 points. Give us as 2.60 kilonewton per meter square, and there's a formula that if you have 2 point loads, the vertical stress delta Z sigma Z sigma Z is equals to the vertical stress caused by the first point 1 plus the vertical stress caused by the second point 2. So just add vertical stress caused by here to get the total vertical stress. So let's do the first one. That's delta sigma Z1. That's I into P over Z squared, blah blah blah. The P is what we're looking for in the first one. That's Q. We don't have it. Just have Q1. The Z is the depth. The depth, like wherever point they are giving you, from the ground surface to that point is Z. So Z is 3 squared. And now I said we can just get, rather than using this long formula, you can just compare. If you use this formula or use the tables, you get the same answer. But I would like to use the tables where you have R over Z. Now R is like a radius. It's the distance between the point load and the points that are taking vertical stress. So it's like when you're calculating moments, the normal CEG structure analysis making some materials, it's just the perpendicular distance from the point load to where you're taking vertical stress. So here is 3 meters, here is 4 meters. That means R here is going to be 7. 7 divided by 3, that's 2 points. 33333, something like that. Then you come from 7 divided by 3. Yeah, 2.33 something. So you just go to the tables. You just go to the tables and you have to interpolate in this case. You check tables, you have only for 2.0 and I think you have for 2.4. So that's 2.4 minus 2.0 equals to x. The value for 2.0 is 0.05058. Sorry, that's a bit small. You can just confirm as you're solving this limit. This is 0.004 minus 0.0058. After you complete and do this, you get x as 0.00463. Just in case you are doubting, I can confirm the same values using this formula. So again, we got our I1 from tables to be 0.00463, where we interpolated between 2.2 and 2.4 to get this value. But in case you want to use the formula, which will waste your time, but in case you want to use this formula, I1 is equal to 3 over 2 pi into 1 over r all over z squared plus 1 raised to 5 over 2. Again, I said r is the radial distance between the force and the point of application where you're calculating vertical stress, and z is the depth. So r here is given as 7 meters from the force q1 to the point A, and the depth from the ground level to the point A is 3. So r here is going to be 7 and z here is going to be 3. When you do this on the calculator, you get 3 over 25 multiplied by 9.485 and 10 raised to the power minus 20. And when you multiply by 3 all over 2 pi, you get something like 0.00453, which is, well, there's some difference, but it's significantly close. I would just like to add that engineer body does not really care about your interpolation. Like, it doesn't care that your interpolation must be so fine. You don't have to use 2.33 or 2.333 to make your answer as fine as possible. Even if you use 2.3, like, it's okay with you. Even if you assume that 2.333 is equal to 2.4, it's okay with you. So you don't have to be so fine when you're calculating in case you don't have time. But if you don't have time, then there's no problem. But for the sake of this tutorial, let's stick with 0.00463 as our I1. So moving on, to get our change vertical stress for the first force. Again, we don't have Q1, so I'm not giving the question. That's what we're looking for. So that will be Q1. Our Z is 3 squared, and our I is 0.00463. Let's just leave this here. Let's go to sigma Z2, which is this force, which was given as 260 kilonewton in the question. So here we have our Q2 to be 260 kilonewton, our Z to still be 3 squared, and our I, which we are going to get from tables again. Again, I is dependent on R over Z. Z and Z at the same thing, 9. So R over Z, this time our R is going to be radial distance from this point to point A. That we are taking it from here to point A, and so it's given us 3 meters in the question. So R over Z is going to be 3 divided by 3. Again, R is from this point of the perpendicular distance from the force to the point you are calculating vertical stress for. So you get 1, and from the tables, this one you don't need to do any calculation since you already have 1 on the table. This is why tables are faster. You get I2 to be equal to 0.0844. Hope everyone is with me. Then just put this back into this formula, 0.0844. After doing the mathematics, you should get that's 260 divided by 3 squared times 0.0844. You should get something like 2.438. Again, this is force all over depth squared. Depth is a meter squared. Kilonewton divided by meter squared is kilonewton per meter squared. It's that simple. R over Z, got 1, check the influence factor dependent on R over Z. You get I2 to be 0.0844. You do the arithmetic calculation here, and you get your Q change in stress for the second force to be equal to this. Earlier I stated that the total change in stress for two forces acting on the soil is equals to the summation of the two forces that cause the stress, the two vertical stresses. So you just adding this and this. I already have the summation of this and this to be given in the question as 2.6. This was given as 2.6 in the question. So if we have this to be equal to we have this to be 2.6. We don't have this, so let's just call it x. And we have this, sorry, the one we just calculated, which was 2.438. So let's just use 2.44. I can find x to be equal to 2.6 minus 2.44, which means my change in vertical stress for the first point is given by 2.6 minus 2.44, which is 0.16 kilonewton per meter squared. Don't forget your units, very important. This is my change in stress for the first force. And earlier we had the formula for this to be equal to same formula, Q1 all over Z squared times I1. Our Q1 is unknown, our Z squared was 3 squared, our I gave us 0.0463. So we have this, we have this, we have this. We can easily find our Q1, which is what the question was asking us for. So Q1 will be equal to change in Z1, that's vertical stress caused by first force, 1 divided by 0.00463 multiplied by the depth squared. We add this to be 0.16. We have 3 squared to be 9, all divided by 0.00463.
Is that what we have?
It's a large force, 311.02 kilonewton per meter squared. So you can see that if you have, this is 311, this is 260. If you have a large force acting very far from the point where you're measuring your vertical stress to, the same way in logic, where if I apply a force on the saw at this point and I check the effect at the end of the book, it will be less than if I apply a lower force very close to the point. That is from 7 meters. The effect that this has, so this is just in kilonewton per meter squared, that this has just gives 0.16. Unlike this, where its effect gave 2.44, because it's very close to the point of application. So that's just for understanding. I think that's all the question asks us for, just to find Q1. Tell me one thing of Q1. So earlier we took a question where we had 2-point loads acting on the soil. We're given the depth at which we had to calculate vertical stress, and we're also given the radial distance r between the two forces and the point we're calculating vertical stress to. I explained that the total vertical stress is summation of vertical stress for each force. We got for the second force, we're not given the magnitude of the first force. We got for the second force, we had the one for the total vertical stress. Just did total vertical stress minus the one for the second force. We got the one for the first one, and we used some mathematics to get our Q1 in that question. In that question, we had just a 2-point loads. So for this second question, number 2C, this question has a lot of calculation. A square footing 3 meter wide is located on the ground surface with the pressure of that. A 4 meter thick clay layer exists at a depth 10 meter below the foundation. Find the average increase in vertical stress at the clay under the center line and edge of the building. So we have a square footing 3 by 3. That means B times L is 3 by 3 meter. We also have the depth that we're taking vertical stress to. Again, the depth is known as Z, which I've written here, which is taken to 10 meters. That's quite large. And we have the pressure. This time it's not a point load, it is a pressure, kilonewton per meter squared. It was clearly stated here that it is a pressure given in small q. Unlike the first question where they said the point loads Q1 and Q2, this second question said the pressure, which is 100 kilonewton per meter squared. So before you start your question, it's very important to draw the diagram. Like in the first question where I did something like this, then to the point A, blah blah blah, you put the depth, put the radial distance, put the radial distance again. So it's very important to draw your diagrams. I think maybe you carry half mark or 1 mark or 2 marks, I don't know. And it's also good for explanation, for you to understand what you are doing. Now this is how the square footing looks like. They say we should calculate the vertical stress under the center line and at the edge of the building. So we know we are going to 10 meter depth. But now this is the plan. Under the center line of the foundation, we have to get vertical stress at this point, and also we have to get vertical stress at this point, at the edge. At the edge of the building, you could have taken it at this point, you could have taken it at this point, you could have taken it at this point. But I decided to use this as my edge. This is just for explanation. This is the plan, and this is like the front view of the foundation. This question has Q in pressure, unlike where we are giving the force, the point load acting on the foundation. We have the pressure, we have the square footing, we have the depth. So let's move. I don't want to clean the second diagram again. Oh, I don't think I've stated it before. When you are calculating vertical stress for a pressure acting on a rectangular or square footing, they usually break them up into triangles. So if you are taking vertical stress for this, let's say a square footing, I want to take vertical stress at this point, I'll break it into a triangle. Like this is already a full triangle, and at the edge, I don't need to break it again. I'll just take vertical stress at this point and use this as, now we have something we call M, or we have something we call N. I'll use this for my N, I'll use this for my N. Don't worry, all this makes sense later. If I have another triangle and they give me this point, I'll break my triangle into this and this, my rectangle rather. So I have rectangle 1, rectangle 2, rectangle 3, rectangle 4. In this case, I only have one rectangle because I'm just taking it at this edge. Once I put it at a different point, once I put it at this point, I'll have 4 rectangles. If I put it outside the point, I'll extend my rectangles like this, so that I have the normal rectangle 1 and the full rectangle here that has this one as 2. In this case, you take this one as a rectangle and you take the full stuff as another rectangle. This whole concept is just to explain to you that vertical stress is always using the length of a rectangle. So when you take it to the center line, that's why I broke it into 4. This rectangle, this rectangle, this rectangle, and this rectangle. But for this point B, I'm only going to use one whole rectangle. This will make sense later. Let me start solving the question. So, unlike where we have point load and just get R and Z, the table for influence factors for this varies a bit. So on that table, you can just check in Aurora, VNS, Multi, or Braja, all of them have the table. So at point A, I have in this diagram, when I take it to the center line and I have a square, I have that all rectangles will be equal. This will be 1.5 by 1.5. That's rectangle 1. Rectangle 2 is 1.5 by 1.5. Rectangle 3 is 1.5 by 1.5. Rectangle 4 is 1.5 by 1.5. The same way in the first case, we had vertical stress, total vertical stress. So we got to be the summation of some vertical stresses. In this place, we have total vertical stress to be summation of the 4 rectangles. And because the 4 rectangles are equal, 1.5 by 1.5, I just have 4 different same rectangles. acted upon by the same Q of 100, it means my vertical stress for each rectangle is going to be the same. My vertical stress Q for each rectangle is going to be the same. That means this is equals to this is equals to this is equals to this, which means I can just do 4 into the vertical stress of any of them. Hope this makes sense. So let's solve for a vertical stress of 1. Now I said there's something known as M and N now. Unlike before we had R over Z straight for point loads. Now we have M and Z. You can take them as any side. M can be your length, N can be your breadth, N can be your breadth, M can be your length. If I have an M value of 1.4 and an N value of 1.6, I have an M value of 1.6 and an N value of 1.4. When you check your tables, these two will give you the same value for influence factor I. So let's take my M as breadth and N as length, just for the sake of this tutorial video. Okay, so my breadth, now instead of R over Z, I have B over Z for M, and instead of R over Z, I have L over Z. Again, I said I'm breaking it into rectangles. So my B now is not the entire breadth of this something, it's the breadth of one rectangle. So let's just call it B prime. My L is not the total length of the, sorry, this time the square. The total length of the square is going to be the length of one square. Let's call it L prime. Z was given the question to be 10 meters. So you have 1.5 divided by 10. And I have 1.5 here also divided by 10, because this is a square 3 by 3 divided into 2 for the center line. 1.5, 1.5. I'll have 0.15 here and 0.15 here. And this is why I don't like this question, because these two values are not in the table, and I have to interpolate for M and I have to interpolate for N. It takes some time. I can clean this for now. So let's go for M first. For M into 0.15, let's solve when N is 0.1. The table looks something like this. You have M values here, you have N values here. So M values will come like this, N values will come like this. Then where they meet, so if you have maybe 1 and 1 here, where they meet at this point, that's the influence factor value. Again, this is just for rectangular, easily loaded or square loaded footings. So here we have our M at 0.15, our N at 0.15. I'm checking through the table. I have a sample of the table with me. We don't have 0.15 on the table. So let's just hold M constant and find 0.15 of N. Since rather than interpolating, we can just add both of them together. One of 0.1 and 0.2 and divide by 2. So for N at 0.1, we have 0.0047. At N at 0.2, we have 0.00917917. I just divide by 2. Again, let's just use M at 0.1. This is M at 0.1 and N at 0.15. Hope you get. I'm leaving M at 0.1. I'm using N at 0.15. So this should give 0.00695, 0.00695. So now let me change the base. Let me use M at 0.2, like 0.1, 0.15, and N at 0.15 again. Okay, I would have on this table 0.00191790, 0.001790. This is for 0.2, and I'll have 0.001917 divided by 2. So this will give me about 0.01355. Make this clear. I think I can clean the diagram. No, that's still in the diagram. 1355. So now this is at 0.2, 0.15. Now to get at 0.15, 0.15, I'll just add, this is for 0.1, this is for 0.2. I'll just add these two values together, divided by 2, and I'll get that. However way you know how to interpolate, you can use it. This is just how I interpolate, and I find it rather fast for me. Again, we're just adding, these are influence factors. Let's just say I1, I2, and this one will be I3, which is what we're looking for, divided by 2. By the time we do this, you should get something like 0.01023. These are our influence factor at 0.15, 0.15. So this is my only problem with this question, the fact that you have to interpolate a lot of times to get a value. So this is the value we are going to keep. Let me just write it by the side. I is equals to 0.010235. How we're doing the other question for a point load, we said that this is equals to P over Z squared multiplied by I, where we had a long formula for I. This was a point load. For a rectangularly loaded footing, change in stress is given by IQ. It's just IQ. We are not doing P over Z squared. In a sense, this P over Z squared is the same thing as Q. So it's just straightforward, the influence factor multiplied by the pressure. So since we have found our influence factor to be this, and again I said to get the total stress, let's just say this is for 1, to get the total stress for the 4 rectangles, seeing that the rectangles are equal and acted upon by the same pressure, you can say that sigma Z1 is equals to the one of sigma Z2 equals to the one of Z3, Z4, which means our total sigma Z can be equal to 4IQ. Hope that is clear. So I have my I as 0.010235, I have my Q to be 100. I can find my change in pressure at the center line below the foundation at 10 meter depth to be equal to, these are mathematical calculations, about 4.094. I've solved this somewhere before, so I'm just picking the values I got. And we have found for the first question, at the center line, again I broke it into 4 rectangles. Rectangles were, sorry, not rectangles now, they're squares. The squares are of the same dimension, obviously, 1.5 by 1.5, 1.5 by 1.5, 1.5 by 1.5, 1.5 by 1.5. In a case where they are not equal, in a case where we have different rectangles, you will still, that means you do IQ for the 4 of them, IQ for the first, IQ for the second, IQ for the third, IQ for the fourth, and add all of them together. But in this case, luckily for us, we have the same types of rectangles everywhere, or the same types of squares everywhere, same dimensions. Again, N and M are just values. They don't really matter in the sense that if N is 1 and M is 2, or N is 2 and M is 1, you get the same thing. So if I have 1.5 by 2 here, and I have 2 by 1.5 here, these two rectangles in this case are still equal. We still get the same influence factor. That's the end of the first part of the question. The second part says you should find it at the point B at the edge of the footing. For this second part, for the first part, I said you take it towards the edge of the rectangle. For this second part, since it's already at the edge, it means my B now, where I have M is equals to B over Z and M is equals to L over Z, I use prime. My B prime now for this second part is going to be from here to this point, which is going to be total 3 meters. And my L is going to be from here to this point, which is going to be total 3 meters too. So I have 3L divided by 10, 3L divided by 10, 0.3, 0.3. For the second part of the question, just to be clear, I don't need 4 rectangles. I have 1 rectangle. I'm taking my vertical stress to this point. My B prime is everything here. My L prime is everything here. 3 meters, 3 meters. unlike when I was taking it to a center point, this is very important. I need to know this. That's what I'm explaining over and over. Where I broke it into 4, which means I have this rectangle 1, this rectangle 2, this rectangle here 3, this rectangle here 4. Where I now took it to the edge of each rectangle. Again, the vertical stress for a rectangularly loaded area is taken to the edge of the rectangles. So where I have the length of this to be 1.5, the breadth of this to be 1.5, this to 1.5, 1.5. I had the same dimension. So I just added all of them together and made it 4 times IQ. But in this case, I just need one rectangle, just one. We're not doing 4 times anything for the second part of the question. So I think we have M and Z on the influence factor table. And if I should just check that, at M0.3, M0.3, I have 0.0, I have my influence factor I to be equal to 0.03735. And my change in vertical stress, as the change in stress when you apply 100 kilonewton per meter square on it, will be equal to IQ, which is just this times 100, 0.03735 times 100, which is 123.735 kilonewton per meter square. Yes. So that's the end of question 2C. Note, vertical stress is taken towards the edge of the rectangle. If it's given at a point that's not the edge, you break the rectangle into the appropriate rectangles rather, not circles. For this case, I have 4 different types of rectangles, which means I'll add the one of this, plus the one of this, plus one of this, plus one of this. In the case where they are the same type of rectangle, you just calculate for 1 and multiply by 4. In the case where you have it to the edge, you have just one rectangle. There's also a last condition where you go beyond the edge of the rectangle. Let me just re-explain that. Where it goes beyond the edge of the rectangle, times I have something like this. Let me give arbitrary values. This space is 2, this space is 4, and they say at 1 meter from the edge. You just draw an extra rectangle here. You calculate. You take this whole rectangle, which is, take this as one rectangle, 5 by 2. You take another rectangle on its own, which will be 1 by 2. We'll solve the question on this to be clear then. So you have the 2 rectangles. This full rectangle will be 1. The full rectangle here will be 1. This rectangle on its own will be 2. So you do this one minus this one. Since one is like you carry this whole thing. The vertical stress you get from this minus vertical stress you get from this alone. In the next question we're going to solve something like this. You can pause the video. Okay, so the last question in 2018 on vertical stress is 2D. It says a flexible loaded rectangular area is as shown in figure question 2D. The uniformly distributed load, this is the figure. Uniform distributed load on flexible area Q is 100 kN per meter square, which is this. Determine the vertical stress increase at a depth 3.5 meter below the area at points B and O respectively, at points B and O respectively. So this is just similar to what we did before, but we have a point that's outside now. Let's do with the first one. So for this point B, as I said before, you divide into rectangles, which means I'll do this, and I'll do this. If I have this to be 4 meter, I have this to be 1.6, what to the left here will be 2.4. If I have this to be 2 meter, and I have to get to be 0.3, what to the left here will be 1.7. So I have 4 rectangles of different dimensions. This is 1.7 by 2.4. The second is 1.6 by 1.7. The third is 0.3, sorry, 2.4 by 0.3. The last one is 1.6 by 0.3. In this case, we can't do what's split to that special already for IQ. In this one, we're going to add the change in stress of this to the change in stress of this to the change in stress of this, change vertical stress of this. Everything together will give me my total vertical stress delta QZ. So let's go. Just have a mental picture of this so you can draw it out, or you can look at it from here. Let's deal with the first rectangle. So for the first rectangle, 1.7 by 2.4, again you can choose anyone as your N and anyone as your Z, as your N rather. I'm using this as B prime over Z, I'm using this as L prime over Z. What I mean is you can use B here or you can use L here. You can do L prime over Z here or B prime over Z. The influence table will still give the same results. So for this tutorial, let's use B for M. So here our B prime for the first rectangle, our B is going to be 1.7. Our Z was given as 3.5 meters. For the L prime, our L prime here is going to be 2.4, and our this is going to be, our depth is the same as 3.5. Depth does not change. When you do this, you should get something like, for the 1.7, I should get something like 0.5. It's not exactly 0.5, but again, and Jambaji does not really care about your interpolation, so I'm just choosing values that are easier to get influence factor immediately. So here, without interpolating, I get my influence factor to be 0.10340. This is an approximation. This is not directly equal to, it's an approximation. So there's no need to interpolate. You just keep this value. Let me make a box right on my eyes. So I have I1 from the table to be 0.10340. And so when you check M at 0.5 and N at 0.7, you get this. That's for rectangle 1. Let me label them 1, 2, 3, 4. So let's do this again for rectangle 2. For rectangle 2, my B prime over Z, my B prime now, this is 2, is still the same 1.7 divided by 3.5, which will give me 0.7. My N, which is L prime over Z, now becomes 1.6 rather than the 2.4 we had earlier. That's 1.6 divided by 3.5, and I should get something like, approximated it again to be 0.5, sorry, this is 0.5. So when I checked I at 0.5, my I2 gave a value of 0.08403. So I've added 3. We'll do this again for rectangle 3, do this again for rectangle 4. For rectangle 3, M is B prime over Z. This is 3. My B now is this place, this height, which is 0.3. My depth does not change, 3.5. And here we're going to do this 0.3 divided by 3.5 gave 0.085. So I'll just approximate 0.085 to become 0.1. Because the stress of interpolation wastes time and you don't get marked for that. N is equals to L prime over Z, which will be 2.4 over 3.5. I think we did something like this earlier. I approximated to 0.7. When you check I under this 2, my I3 will give me a value of 0.02420. That is 0.0242. And the last part, that's I4, we have our M to be B prime over Z. For this fourth one, my B is going to be 0.3. My depth does not change, 3.5. We did this earlier, we had 0.1 or 0.085 and approximated 0.085 and approximated to 0.1 rather than interpolating, because 0.085 is not on the influence chart, the influence table, influence factor table. So n here, that's L prime over Z. My L prime is this is 1.6, or divided by 3.5. The exact value will give 0.457. But this will waste my time and I have to interpolate. I can't approximate this to get 0.5. Hope you have with me. When you check this on the influence factor table, my I4 will be 0.01978. So seeing that we have all our eyes, change the stress for the first rectangle where it is rectangularly loaded with a pressure, not a point load, is IQ. And our I is 100, just multiply 100 by this. I should get 10.340. For the second one, IQ again, let's say I1Q, I2Q, that's 100 times this, 1, 2, that's 8.403. Again, the unit is in kilonewton per meter square, kilonewton per meter square. For the third one, it's just going to be I3Q. We have our I3 to be 0.02420 2 times 100, which will be 2.42 kilonewton per meter square. And for the last one, I have 100 times 0.01978, which just give me 1.978 kilonewton per meter square. So to get my total vertical stress at this point B of this rectangularly loaded area, it's just the summation of all these four. 1, 2, 3, 4. So I'll have 10.34 plus 8.403 plus 2.42 plus 1.978, and this should give me about 23.141 kilonewton per meter square. So at the point B, at a depth 3 points, where the depth Z is equal to 3.5 meters. When it is loaded with 100 kilonewton per meter square, at this point I'll get my change in vertical stress, the effect of the load on this foundation at the depth 3.5 meter. It changes the vertical stress by 23.141 kilonewton per meter square. Same process, break it into rectangles, go to the edge of the rectangles, take that as a B prime, take this as a L prime. So that's the end of the first part of the question. Second part says we should get it at O. So let's do that. In the earlier question, I explained how you get change the vertical stress outside the rectangle. But in case it didn't make sense, then let's solve the question on it. I said you extend the rectangle at first. My drawing, I'm not good at anything that involves drawing or art. Quite useless actually. So this total length is going to become 4 meter plus 1.2, which is 5.2 meter. Right, I think you should be able to see this. So I said you have two rectangles. The big rectangle, which will be 5.2 and 2 meters. And we're going to have the small rectangle, which will be 1.2 meters by 2 meters. So the logic behind this is, for this rectangle 1, you find change the vertical stress. For this rectangle 2, you find change the vertical stress. Then you subtract 2 from 1, which is like you are cutting out this part from this rectangle, which will give you the normal footing itself. That's the logic for when you are looking for vertical stress at a point outside the footing, outside the foundation, outside the 4x2. You find for the big rectangle subtracted by the one for the small rectangle. In this place now, we can see that our L is going to be 5.2, here is going to be 2, our L here will be 1.2, our B here is going to be 2. So it's quite straightforward actually. M for the first rectangle, this one is for the entire part, this 2 is on its own. For the first rectangle, I'll have B prime over Z. My B prime will be 5.2 here, the entire length. All over my depth is still 3.5, doesn't change. Q is still 100. And my N is L prime over Z. My L prime is 2, unaffected, all divided by depth, which does not change, 3.5. So when I approximated for this, I got 2 over 3.5 to be something like 0.6. This is an approximation, so I don't have to interpolate. And N 5.2 over 3.5, I approximated this to give me 1.5. So when I check these two on the influence factor table, I found my I1 to be. Oh, I still have to interpolate because there's no 1.5, so I have to interpolate between 1 and 2. But since 1.5 is the middle, I just decided to add both of them together divided by 2. So for m is equals to 1, you will see for m is equals to 1 and n is equals to 0.6, you will see your influence factor to be 0.14749. And for m is equals to 2 and n is equals to 0.6, you see your influence factor to be equal to 0.15028. And when I divide this by 2, I'll get 1 for 1.5. So after doing this, I'll get my influence factor to be 0.1488885. Not that long. And my final change in stress for the first one is just I1Q. When my Q is 100, multiply this twice, I have 14.89 kilonewton per meter square. Hope this is clear. Lastly, for the second rectangle, I have M B prime over Z. I believe you should know that B prime now should be 1.2. My Z is 3.5. For my M, which is L prime over Z, my L prime here should be 2, 3.5. Same approximation, 0.6. 1.2 divided by 3.5. I should get an approximation that is close to 0.3. I can easily find my influence factor this way. No need for interpolation in the second part, 0.06294. And to find my change in stress, vertical stress, for the second part, just multiply I2Q. This is this times 100, because Q is 100 kilonewton per meter square in the question. So this is 6.294 kilonewton per meter square. Again, I said for where the point is outside the footing, your change in vertical stress, total change, will be equal to change in vertical stress of the full rectangle minus change in vertical stress of the smaller rectangle inside. So when you do this, you have 14.89 minus 6.29. I have something like 8.6 kilonewton per meter square. You're just subtracting this from this. That's the end. I've done vertical stresses for 2017, 2018. I would like to solve for 2014, 2015 just for clarity, so that we have more than one example to use, more than 1 year to use. So let's go to 2015. So in terms of 2018, for the first part, we solved a question on vertical stresses where we had 2-point loads, and we're taking our vertical stress to a point. We found our radial distance r to be the perpendicular distance between the forces at that point. We had our depth z to be the depth between the ground level and the point we are taking vertical stress to. Secondly, we solved a question on the rectangular or square loaded area where we are not given a point load, and our change in vertical stress was something like this, what I can remember. For the first one, we had our change in vertical stress for a point load to look like something like this. Multiplying I, where we had I as one long formula that had I into 1 all over r over z square plus 1 blah 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 5 over 2. No matter blah, but you can learn this, so I advise you learn this. You can also use tables to just find this. So we did for point load, we did for rectangular loaded area, we did for rectangular loaded area at the center, we did for rectangular loaded area at the point that's not the center, we did for rectangular loaded area outside the rectangle. In this next set of questions, we're just doing for at least 2B, we're just doing for a point load, which means this formula is not needed. The formula I'm working with is this. So let's read the question out. 2014-2015, number 2B. 3-point loads, 8,000 kilonewton, 9,500 kilonewton, 6,000 kilonewton, act in line 3 meters apart, which means that these three forces are 3 meters apart from each other. Near the surface of a sole mass. Calculate the vertical stress at a depth 6 meters vertically below the center beneath the 9,500 kilonewton load using the business equation. This is the business equation. At a point 6 meters below the 9,500, we are taking vertical stress to this point. For this 8,000, my R is going to be 3. For this 6,000, my R is going to be 3. I think you can guess that for this 9,500, R is going to be 0 because there's no perpendicular distance. It's like just taking moment, as I said before. Moment is the first and the perpendicular distance. For this point, there's no perpendicular distance. It's acting the same line of action. So R is 0 for 9,500 kilonewton. Let's move. Our total vertical stress again will be the summation of the vertical stress of this 8,000 kilonewton plus the vertical stress of the 9,500 kilonewton plus vertical stress of the 6,000 kilonewton. This was fly for 8,000 kilonewton. That's change the vertical stress of the first one. It's going to be P over Z square. P is the point load, 8,000 over Z square. Our depth is still going to be the same 6 meters. Multiplied by I. Now I is dependent on R over Z for a point load. It's dependent on M and N for rectangular loaded area where it's loaded by a pressure in kilonewton per meter square. When it is loaded by just the point load, R influence factor is dependent on R over Z. So there are two different tables. So R over Z here, my R is going to be 3 meters, my Z is going to be 6. This is nice, we don't have to interpolate. 0.5 and dots. So when you check the influence factor table, I1 should give a value of 0.2723. 2733 rather. and we just multiply this by 0.2733. So this should come back down here. And you have a change in vertical stress for the 8000 kilonewton to give something like 60.73 kilonewton per meter square. So we have for the first one, let me just write it somewhere here. For one is 60.73 kilonewton per meter square. For the second one, we'll just be changing values here. 2 changes I, changes to be 9,500. For this second force, 9,500, the depth is the same, 6 square. And the influence factor now, R over Z, which is dependent on R over Z. My R for the second one, as I explained earlier, will be 0. There's no distance between the force and the point of action. There's no distance, so R is 0. Our Z is still 6. This should give 0. Checking the influence factor is at 0. You have, I think, 0. I2 should be 0.4775. Just multiply this by 0.4775, and you get your change in vertical stress of 126 kilonewton per meter square. This comes down all the way here. So let's just store this somewhere. 126 kilonewton per meter square. I particularly like this vertical stresses. I think it's the most straightforward part of this course. Everything in this course is not balanced. However, at least for point loads, this is very straightforward. For change, for the third one, that's for 6,000 kilonewton. P over Z square, P is 6,000. Z is still 6 square. We're looking for I. R is dependent on R over Z. My R is 3 meters, and Z is still 6. I have 0.5. I have the same I had earlier, 0.2733. So I multiply by 0.2733, and I have my base to come down here. When you do the multiplication, of course, you get something like 45.55 kilonewton per meter square. So let's just keep this third one here, 45.55 kilonewton per meter square. While the 9,500 is larger, but I can tell you that if this was 8,000, 8,000, 8,000, the one in the middle that's acting directly on this point will have a larger effect. I'm sure you can see that 126 is far greater, it's 2 times greater than this, nearly 3 times greater than 6,000, and the force is just 1,500 kN, same difference. It shows that when you apply force at a point, and you take the vertical stress at that same point to the maximum, it means that the smaller your R is, the more your R tends to 0. The greater your vertical stress is, the D. So to get our total vertical stress from these 3 forces, I'm just going to be adding these 3 together. The first one is 60.73, the second is 126, and the third is 45.55. So when you do the arithmetic, you should get something like, this is looking like 232.28 kilonewton per meter square. And this is very important, don't forget. Point load again, 3 point loads. Add 3 of them together. We found for this, one for this, one for this. Influence factor I for a point load is dependent on R over Z. We found all our influence factors, multiply them by the P over Z square. We got these 3, added them together. That's the end of this question. You can pause. Okay. Question 2C says, rectangular foundation 8 meter by 12 meter. 8 meter by 12 meters. Carries a uniform pressure of 300 kilonewton per meter square. Just like to add that if you put your 12 meters here and your 8 meters here, you still have the same value for your influence factor. So again, rectangular foundation 8 meter by 12 meter carries a uniform pressure of 300 kilonewton per meter square near the surface of the soil mass. Determine the vertical stress at a depth 3 meter below a point on the center line and 2 meter and 2.5 meter outside a long edge of the foundation using influence factors. Let's say this is the long edge and this is 2.5 meters from the long edge. So for the first one, they said below a point on the center line, that's in the middle. Similar to the old one we did, divide into 4. If I do that, I'll have 4 meters here, 4 meters here, 6, 6, which used to be 4 by 6, 4 by 6, 4 by 6, 4 by 6, which means they have the same dimensions. And if they have the same dimensions under the same load, we'll have our total change in vertical stress to be equals to 4IQ. So to get I, we know we have M and N. Our M is equals to B prime over Z, and our N is equals L prime over Z. So let's say our B prime is 4 divided by 3. We should give 1.33, but let me use 1.3. And this would be 6, 4 divided by 3. Should give 2. Let me check. It's 1.3 on that paper. I don't think 1.3 is on the factor table. 1 second. 1.3 is not there. Let me just use 1.4. Approximate this as 1.4. So I don't interpolate. So when I do this, I get my influence factor I to be equals to, again, I1 will be equals to I2, will be equals to I3, will be equals to I4, will be equals to just I, since we are using this formula. So our I at 1.4 and 0.2 will be 1.4 and 2, I'm saying 0.22058. Pardon me that this is small, write out larger somewhere. So to calculate this, I will have 4 by 300 by 0.22058. It should be quite larger. I've not solved this question before, so permit me to do the calculation here. That's 264.7 kilonewton per meter square, and that was all for the first part of the question. At the center line, 4 rectangles of the same dimension, 4IQ. If it was at a different point, say you do it 4 times, but now at the center, before equal rectangles, we found our M and N, we found the influence factor, and we did this. So the second part of the question, which is the final one I'll be solving, is at a point 2.5 meter from the long edge. Again, same thing I said, where you have to extend this rectangle. So let's extend this rectangle to that point. Still have this, still have this, still have this, and still have this. We have rectangle 1 and rectangle 2. Rectangle 1 includes rectangle 2. That is, rectangle 2 is inside rectangle 1. And rectangle 2 stays on its own. Our total influence, our total change in vertical stress will be equal to change in vertical stress of rectangle 1 minus change in vertical stress of the second rectangle. So to get to the first one, we have agreed that for a rectangular loaded area, this is the formula. We have our Q as 300 now to find I. So for the first one, to get our M, which is B prime over Z, I think it's the last time I have to say this. If you use B prime over Z or L prime over Z, for this, and if you interchange the values basically of m and n and check your influence table, it is the same thing. Don't mind how I put my B or I put my L. But for the sake of this tutorial, I'm using B for M. So let's say my breadth for this long rectangle will be 12.2.5. Let's take it at the edge. 12.2.5 is 14.5, all divided by, what's my Z? My Z is, the depth was given as 3 meters, right? Yeah, 3 meters. And this second part will be 8 divided by 3. Which should give 2.67. 2.67. Which one work for you? I can approximate this to 2.5 or something. So this the original answer is 2.67, but because I don't interpolate, I'm using 2.5. 14.5 divided by 3. 4.83. I could use 5 for this part, 5.0. So to get the influence factor at 5.0 and 2.5, I should have something like 0.24392. I1 is equal to 0.24392. Let me just find a place to store it. I1 is equals to 0.24392. We'll do this again for the second rectangle, which is the smaller rectangle now. So that's the second rectangle. That'll be I2 cubed. Our B prime now will just be, our B prime here will still be 8 over 3. Let's take this as, where am I using our B prime? Anyhow, they share the same thing. Let me just be consistent. Maybe 2.5 divided by 3. And this will be 8 divided by 3. I'm taking this as 2.5. 2.5 divided by 3 should give 0.83. Let me just take this as 1. So I'm checking 1 and 2.5. From the table, 1 and 2.5 gives something like I2 should be equals to 0.20236. So I'll just keep this here. I2 0.20236. Yes. So finally, to get my change in my total vertical stress, this first one is I1Q, which is this 0.24392 times my Q, which is 300. My second one is equals to I2Q, which is 0.20236 by 300. 2492 by 300. 73.18 kilonewton per meter square. This is 60.71 kilonewton per meter squared. And lastly, to get the total change in vertical stress, I'll have 73.18 minus 60.71. 73.18 minus 60.71 gives 12.47 kilonewton per meter square as my total change in vertical stress at the point that's 2.5 meters from the long edge of the footing from the foundation. Which brings me to the end of vertical stresses. So just one last recap before I close. This is the end, this is the final answer we're looking for. For this course, our vertical stresses involve a point load or a uniformly distributed load acting on a rectangularly loaded area. So we either have a point load acting on the cell surface with the radial distance and at a depth from the ground level, or we have a UDL. Sorry, not a UDL, a pressure rather. A pressure acting on the footing. This is the front view, something that looks like this. This is the plan, where you either choose the center, the edge, outside, any point. But the logic is you divide into rectangles. If they are equal, for IQ. If they are not equal, just IQ. So for this, our change in vertical stress is just IQ, depending on the kind of question you are given. For this point load, our change in vertical stress is, let's say Q now, Q over Z squared multiplied by I. The I here is dependent on R over Z, while the I here is dependent on M and N, where M is B prime over Z, M is L prime over Z. So I think, let me just add this last T. If it's at this edge, it's on before IQ. You have to break it into these four respective rectangles and add them together. So you will be adding if you have something at this point, I have 1, 2, 3, 4. You'll be adding the vertical stress, change the vertical stress for 1 plus 1 of 2 plus 1 of 3 plus 1 of 4 to get the total change in vertical stress. If it is outside, you have two rectangles and you're having the big rectangle minus the one of the smaller rectangle, the one we just solved right now. I think that's all we need for vertical stresses. So it has been nice teaching people. I'm tired. Thank you.